Okay, so my name is Péter Simon, or Espeti as my nickname from Discord. So I am an electrical engineer. I just finished my master's degree, and I work in the embedded field. I both hardware and software development, and I also occasionally work with safety critical systems. So that's why I chose this topic, and I like airplanes. So first, let's start with what is functional safety itself. This is basically a way to ensure that a certain system, an electronic or electrical system, uh, has a predictable probability of failure. Uh, and it is also designed to fail in a safe way if it fails. And this both applies to hardware and software. And it has two main categories. There are safety critical systems and mission critical systems. The difference between these is that safety critical systems can be designed in a way that they have what's known as a safe state. Uh, so they can stop operation in a way that is safe. Uh, for example, I'm working on an overspeed governor for an elevator, and basically there is a safe state when you apply the brakes. If anything fails, you can always just engage the brakes and it will stop and everything will stay safe. However, if you are, let's say, want to make a flight control system for an aircraft, you can just stop in the air. So there's no safe state in that case. So you need to continue some kind of operation, uh, either fully functional or reduced operation, in case of a failure. And that is what a mission critical system is. So basically, there are a few standards for these. The most commonly used is the 61508, and there's an automotive variant for this that is largely the same. And there are these are less similar, but basically cover the same main topics in the aerospace industry. And the MISRA-C is also a common standard that we use in safety critical systems. It is basically a rule set for the C language that make it less prone to coding errors, basically. So for the main goals of functional safety itself and its design process is it it basically covers the full life cycle of either a hardware or a software development. And first of all, you need to evaluate what risk and assess what risks you have in your system. What safety mechanisms can you use? And such systems also include fault detection, so they can detect certain problems that might not cause a failure by themselves, but will be a problem later on. And it also covers the entire life cycles of the hardware and software design. So it has a lot of areas that I won't cover it now because it's quite complicated. So basically, the 61508 standard defines these safety integrity level categories that that basically represent the probability of failure uh, that we want to expect from such a system. And this probability that I listed here is basically the inverse of mean time to failure, uh, because in this standard is mostly referred to as a probability. And you can notice that I have two different representations for these. Uh, they're basically somewhat the same priority, but one is expressed in probability of failure in during 1 year and in 1 hour. Uh, this is because of certain systems might work in different way. For example, if you have a system that operates continuously, then you use the hour representation. But let's say you have an ECU in a car that controls an airbag. The ECU itself is continuously operating, but it only has to deploy the airbag sometimes. So, so that's where you use the low demand mode representation to express the probability of failure of those systems. And this is a risk matrix for how to and the different considerations in how to choose what you of what safety integrity level you need. You can just take a look at it, but basically uh, you have to take into account the consequences of and how rare or infrequent uh, a dangerous event is likely to occur, if it's avoidable, and what probability will it occur with. But these have uh, these have quite vague definitions or not. I shouldn't say vague, but many different kinds of interpretations in the 61508 standard. So, how do we make airplanes safe with all of these? First, I want to start with the basics before I get into the safety part of this. So you can understand how airplanes actually work, and so you know what I'm about to talk about. Just a moment. So first of all, I want to thank my teacher, Schuster George, for providing these slides for me. Uh, because we also had a lecture about this at the university. So this is basically the history of different Airbus series. We are gonna talk about the A320 that first came out in '87, and this was Airbus's first fly-by-wire system equipped aircraft. And after that came the and this is the pretty much the from the A320 onwards are the aircrafts that are still in service today, basically. So there's the A320 family, the slightly wider A330, the even wider A340 with 4 engines, And there is the A350, which is a similar size but with two more modern engines. The A380, you know that, and the A320 that came out just a bit over 10 years ago. Uh, that is actually a lot a lot different from the all the previous series in terms of its. Even if you just walk into the cockpit, if you are not familiar with the type itself, just with Airbus cockpits, you wouldn't think it's an Airbus first. That's how different they are. Yeah, so this is the A320. Here are some of the basic parameters of that. Sorry, I forgot to say that the slides are these slides are in Hungarian. I will tell of what you can see in English, but the benefit of this is that for the Hungarian listeners that you will be also familiar with the Hungarian terminologies as well. So originally it came with the CFM and the IEA 2500 engines. It is also referred as the CEO versions, the conventional engine options, and this is the Neo that are produced today, the new engine option versions. That basically comes with bigger and more efficient engines, but it's pretty much the same, and all the onboard systems work in exactly the same way. The smallest member of the A320 family is the A318. Well, it is actually quite rare. You have to be really lucky to find one out there. But this is a really small one. And there is the A319 that is somewhat more common, but and it also has a Neo version. The most commonly used ones are the A320 and the larger A321. And the A321 Neo is also the largest of the series. You can, I'm not sure how well it shows on the projector, but you can compare the sizes of each of these. And here are some of uh, the basic things to note about the A320. Uh, well, it says 150 passengers. Actually, an economy class A320 is in, in practice it is configured for, I believe it's 183 seats actually, because it's packed more tighter than the original designs, and the 321 is 200 is for 230 passengers. These are the some of the sizes of the 320, and let's go to the actual flight controls. So the basics of I already talked that this was Airbus's first fly-by-wire aircraft. What that means is that there is no direct mechanical connection between the flight controls and the actual control surfaces of the aircraft. It is all connected electronically through different computers. Uh, as you will later see, and my teacher also said that one of his famous sayings is that the A320 is really not really just an aircraft. It's basically a flying computer cluster. So here are the control surfaces. uh, you have these are the called the slats on the front. The flaps. That Hungarian name is not exactly describes it what it really does. Mi a féklapoknak hívjuk magyarul, de valójában nem a fékezés az elsődleges feladata. So the the main purpose is for the flaps is not really braking. To describe it in simpler terms, if you extend these, it basically makes the wings bigger, and so it lowers the operational speed range of the aircraft, so it can fly slower. And it also has some additional drag as a side effect. These are the spoilers that are actually for braking. These provide additional drag, and they also basically break the airfoil and make the effective surface area of the wing smaller. The ailerons, and that's the rudder on the back. The horizontal stabilizers with gray, and the elevator. So, well, probably a lot of you are still confused at how it actually all works together. So let's go back a little bit to the basics again. So how do you keep an aircraft in the air? So basically, first of all, of course you have the main wings that support the weight of the hull. Uh, but the problem with these alone is that you can always place them exactly in because the center of the gravity of the aircraft is always changing a little bit. So it is actually placed a little bit further, and so it would naturally want to tip backwards. And there are the horizontal stabilizers that basically balance it out. So it holds the weight on a little bit of weight on the back of the hull. Uh, so yeah, you can now basically stay in the air. You also want to keep it straight, so you need a vertical stabilizer, so it will always point straight, like basically the tail of a windmill. So the air keeps the hull straight, and you may also want to pitch the aircraft like up and down. That's what you have the elevators for, and because of the center of gravity is not exactly always at the same place, you would normally have to hold it with the elevators, so that's why the horizontal stabilizers are trimmable. There are trim wheels that you can adjust the angle of the horizontal stabilizers with those, so you can always balance it out under different conditions. So, okay, then how do you turn with the aircraft? But this is a bit complicated because, well, first you like when you want to turn with a ship or a water vessel, you have a rudder, of course. You also have a rudder here, but it won't be enough on its own because you don't have any flight surfaces that can provide the centrifugal force for the turning. So you have to use the ailerons to bank the aircraft and turn like that. If I don't know if how many of you remembers or how you can fly airplanes in GTA 5. Well, in real life you can just turn like sideways with the rudders alone, like there. So you have to bank the aircraft with the ailerons to provide that to provide that centrifugal force that makes it possible to turn. And you then coordinate the turn with the rudders. As I said earlier, you also have the spoilers that, or not the spoilers are uh, for slowing down after landing. The flaps are the more important ones. Like I said, if you extend them, it basically lowers the operational speed range of the aircraft, so it can fly slower, or allow it to operate slower. And on modern airliners like the A320, it also they are controlled to help the ailerons a little bit. And you also have the sleds that are basically they also the same. The purpose of those is the same as with the flaps. They are just at the front and they help a bit over there. So let's continue with how the control system works here. First of you have these are the different computers you have on board. It's really hard to read there. I'm sorry for that. Uh, you have the flight augmentation computer. As you can notice, there are two of these for redundancy, and that's just, of course, it's not the only redundancy. There are many more things here to make this fail-safe. The the elevator and aileron computers. Uh, I also want to go to point back at this point of the basics of safety critical systems. That how do you join? For example, if you have two of these computers in parallel, how do you uh, how do you produce one output from the from the each of their outputs? Where basically you have to implement something called as a voting logic that that compares the either compares the two outputs, or it can be something as simple. If you have like in a simpler system, you have two microcontrollers together. You can also place a logic gate to the two output to combine their outputs, but that can also fail on its own. So typically you would use something like an open drain output to connect the two outputs in parallel, uh, and then the safe state has to be the pull down state for the system. Uh, s there is also the spoiler and elevator computer. You may notice that there are three of these. When you want to combine three of the outputs of three of such systems, it gets a little complicated. Uh, it is not the exact implementation here, but in general, you have something called a 2 out of 3 operation, where you need to valid outputs or inputs from let's say sensors out of the three existing one to continue operation. So in case of one fails, not only you can continue the operation of the system, but you also still have the ability to detect further failures and react to them accordingly. There's the flight data concentrator. Uh, So yeah, these are the different inputs to those computers. There is an inertial measurement unit called the ADIRU, uh, a flight management computer. Some of these accelerometers, the landing gear control systems, the radio altimeter that you use for landing. There are many ways to. I won't dive really deep into this. You can measure altitude in many different ways. This is one of them. It's basically a radar that works up to 2,500 feet above the ground, and it helps with landing to measure altitude accurately. There's the flap controller, and yeah, that was the hydraulics. Uh, One thing that I want to also point out is that in such safety critical systems, as I mentioned, you have to not only have the computers themselves redundant, but also the sensors. Uh, you may probably remember the uh, what happened with the what was the problem with the Boeing 737 MAX 8. The problem there was that there are many protections in these aircrafts to if you're flying them manually. There are many limits to their operations. For example, one of these is a stall protection, or on the Airbus it is called the alpha floor protection. Uh, it is basically a safety system that prevents the aircraft from stalling and automatically limits the pitch angle and controls the throttle to do this. And it detects a stall with from the on one hand from the airspeed, and on the other hand from the there is some so-called angle of attack sensor. Uh, it is the angle of attack is uh, the angle of attack is the angle at which the oncoming wind is is colliding basically with the wings, because it defines how much lift they can generate. So that is a very important factor to detect stall. So on the 737 Max 8, uh, of course you had two of the yeah, you have two of these sensors on both sides, but I can't really imagine how it got past the all the verifications and FAA, but somehow they only used one of them, one of their signals to detect a stall. And the problem was that some of these sensors, some of these sensors on these aircrafts failed, and they they basically gave out a reading in full deflection in in one way, and the systems the computer somehow uh, wasn't made to verify that this is a false input, and it basically started to trim the aircraft nose up all the way. And one of the problems, and then you, of course, it eventually led to a stall, uh, and they fell down because there's no simple way. You, the problem was that you can correct this, but the problem was that many of these incidents happened happened just after takeoff, when you don't have much altitude, and uh, the trim is actually adjusted with so-called trim wheels. The maximum deflection of the vertical stabilizers is like, I don't know the exact value on the 737, but it's somewhere between 5 to 10 degrees. And there are these trim wheels that would normally are driven by motors that basically move them through hydraulics. And there are electric motors that turn the actual trim wheels in the cockpit. And they are all either controlled automatically or with a little switch on the yoke. And the problem there was that even if you're flying the aircraft manually, you can't just simply override this. So in that case, the only option you pretty much have left is there is a cutout switch for the trim motors that you need to use to shut off the motors. The trim wheels have a little turn handle that you have to fold out and crank it backwards, but it only like adjusts the vertical stabilizers with like half a degree for each turn. So it's not a fast process. And again, the pilots wasn't ready for such a failure. So yeah, it led to several accidents. This is the hydraulic systems of the A320. I will go deeper into this later if we have time. You have basically, for redundancy, you have three different systems: the green, blue, and yellow hydraulics, and each critical, or basically all of the flight control surfaces are can be independently controlled by each of these hydraulic systems, and uh, there are multiple power sources that can feed these hydraulic systems, and they are not interconnected in a direct way, like the hydraulic fluid can't go from one to the other system. They are all separated, but there is a power transfer between them. As I mentioned, the SEC and the ELAC controls the elevators, and this is the you can see here the hydraulic motors that are mentioned earlier that are connected from the trim wheels, and it can be controlled by the side stick. Of course, you know that Airbus's fly-by-wire aircraft use a side stick, not a yoke. Or yeah, by the autopilot. So these are the basic configurations for these the elevators. Normally it is the ELAC that controls the elevators, but in case of a failure, there's two of them, but in case of some major failure over there, the SEC can take over this role, and you can still control the elevators through the side stick. This is the trim system. Yeah, so these are the limits to the. It's not really readable, but uh, the the elevators themselves can be controlled from negative 70 to positive 30 degrees, and the horizontal stabilizer itself can be trimmed from -4 to 13.5 degrees. This is also the there's another representation of of the pitch control basically, and what these are all the inputs it has, and this what these two different computer systems need to work with. And as I mentioned, here there's also you can call this also a voting logic, but this is in the hydraulic systems themselves actually. So there are such systems between the computers themselves and also the hydraulics. One thing I forgot to mention for increased safety in such systems, uh, you not only just have, like for example, when you have maybe in a CO3 or CO4 product, you may use two microcontrollers for redundancy, but a good practice even in CO3, and it is a requirement in CO4, that that having just two of them is not enough by itself. You have to use at least two different, two independently developed software for each of the microcontrollers built on the same requirements. And also, sometimes you should use two different microcontrollers, so they're not even the same type. And in the aviation industry, these all of these computers are like little plug-in rack modules in the aircraft, and these are some of these, like the SEC or ILEC 1 and 2, are actually developed by two entirely different companies. For and they use their own implementations for each of them, and they build for the same specifications. To so you are less likely to have the same failure in both of them at the same time. Yeah, so this is the pitch control, or not? Sorry, not the pitch control. Is the this is the bank control. So again, you have the elect that is mainly in charge here to control the spoilers and or the ailerons, and the spoilers are actually, as I said in the beginning, in normal operations the spoilers are also moved a little bit to help with to help the ailerons with turning. So these are controlled by the SEC, and they use the damping for when both of those fails, and the SEC can take over the or they can they normally don't do that operation for turning. So yeah, this is again the same list of inputs and the outputs, the hydraulic logic between the two systems, and this is the rudder control. Uh, Again, this is also well, normally on the A320 and uh, all of these modern aircrafts, basically, you don't always have to actually use the rudder pedals for turning, like on a small airplane. They are most of the time controlled automatically, and you only need the side stick for turning. and so you don't have to manually coordinate your turning. As you can see, even the hydraulic motors, there are two of them for each of them, and there is also force feedback for the rudder pedals. Yeah, so basically that controls it handles the pedals, the ailerons, and turn control surfaces, and the rudder can also be operated mechanically. If or that is a There is a mechanical link from the rudder pedals to the actual hydraulic valves of the rudder. And there's again also the same thing I showed earlier. I showed that parameter earlier, yeah, and this is the maximum deflection of the ailerons, uh, the spoilers in manual control or autopilot control, and this is also limited by this is the calibrated airspeed, or basically you might be more familiar with the indicated airspeed. Yeah, just a lot of different ways to measure speed. I won't go into that, but it allows for less deflection if you are faster, basically. And these are the load limits for the aircraft. Positive 2.5 to negative 1 G in the normal configuration. The configurations uh, for how much you can pitch, and the bank limits, and the speed limits. It says that there is an alarm if you were to go into an overspeed condition, or the maximum certified speed for the A320 is 350 knots indicated, and but there is also a separate protection that kicks in before even that could happen. Uh, I will just pass on these ones. Not really. And you have the ecam panel where you can select the flight control display option, and these are the drawings that you can see there. And one more thing I wanted to show you a little bit more is the hydraulic system. Uh, Sorry, it's not at the beginning. So these are again, I'm sorry, it's not really readable, but these are the different, the three main hydraulic systems. This is the green one here that has the pump from engine number 1. And this is as I said, there's power transfer possible between the hydraulic systems. There are basically two bidirectional pumps connected to each other. So one hydraulic system can transfer power to the other one, called the PTU, the power transfer unit. Uh, there is the blue hydraulics that is normally controlled by electronic pump, and can be also powered by the Remer turbine that also has a hydraulic pump. And there's the yellow system from engine number 2. This loop controls some systems that are are important on the ground. That's why they usually start with starting one engine number two when they start up the engines. You may also notice there's a hand pump on this system, but that's not for the entire yellow hydraulic system. It's only for operating the cargo door where there is no other power source available. Yeah, there's the reservoir. Just, yeah, that's the PTU I said earlier. And all of those, there's the Remer turbine. Uh, Basically, it has, as I said, a hydraulic pump and also has an electric generator that has a capacity of 5 kilowatts. And this is for when you lose basically both engines and the APU, and because there are also batteries on board, but those are really small to power everything. And you have the Remer turbine to power just the essentials. Uh, yeah, that's the yellow hydraulics, the pump from engine number two, and the hand pump. I just quickly go over these. That's the This is the upper section that you can see in the center. Is the upper section on the upper panel, where you can find these are in the center are the most important circuit breakers, and next to that there's the some of the service or maintenance options for it. Is not the main control panel for the hydraulics, because that is located just below the breaker panel, the lower section of the upper panel, and this is on the top where you have the buttons to control it, and on the down on the center pedestal you have the ECAMS button for the hydraulic system. If you press that, then the ECAM display will show the status of the hydraulic system here again. And let's just quickly go over the electrical system as well. So this is the sorry, yeah, you can see it now. So this is the electrical supply system of the A320. These are down at the bottom. You have the power sources, the main power sources, the generator from engine number one and engine number two, the APU's generator, and the ground power input. All the engines, including the APU, have a capacity of 90 kilovolt amps on the generator, and each of those on their own can operate the whole electrical system with full functionality. They are normally operated by both. There are two AC power buses for redundancy, and they are in a normal configuration. They are supplied independently from engine number one and number two. There's a crossfeed between these inputs, but there's one important thing to know that the generators from engine number one, number two can power the two AC buses independently at the same time, but they cannot be interconnected because there's no way to synchronize them. So there are two transformers. Yeah, so I forgot that this is here. Uh, these are all of them are 90 kilovolt amps. Uh, It says 200 volts also, but it's pretty much in all cases it's a 115 volt system at 400 hertz, because that's a general frequency for aircraft power systems. It simply comes from the fact that basically you have really fast spinning generators, and they generate a or it's a lot easier to produce a high frequency. And also with 400 hertz you can use much smaller AC transformers as well. This is the DC system. There are two DC to AC converters. This is a 28 volt DC system, and this is the main bus for the batteries. They are the most essential systems are connected, or actually it's connected to the DC essential systems bus down here. But as I said earlier, actually there are these two batteries, but they are only 23 amp hours. So that's not a lot of energy you have there. You have 22 minutes to power the really most essential stuff. That's why you need the Remer turbine as well, if in case anything else fails. There's a generator from engine number 1 number to the APU, the external power. The emergency generator it's in the Remer turbine. The two AC buses, the AC essential systems buses. For those systems, uh, there are the DC buses, the essential DC bus, and the two hot buses. Basically the two buses for the direct that are in direct contact with the battery. Uh, there are the two battery contactors on the top here. You can see that you can operate with the two battery switches in the middle of the electrical control panel. Basically, that's what you start with when you are powering up an aircraft, a fully dark aircraft, to connect the batteries first. I don't want to dive pretty deep into this. There are the AC to DC converters. The two of them. There's an emergency AC to DC, or the essential AC to DC converter that is for the Remer turbine, and there is also an inverter if you really don't have any AC power and you only have the batteries. You can power some of the most essential AC power systems with an inverter, but that one is only rated for 1 kilowatts. I mean, you don't even have really large capacity on the barrel. So these are basically the same things that I told you earlier. Just quickly go over these, and that's the electrical panel in the bottom of the lower section of the upper panel in the middle. That's where you have these are the two switches for each of the batteries, their voltage display, and here you can configure the input sources, basically the uh, switches for the two engines generators and the APUs and the external power source. On the eCam display selector panel, you also have the elect button, and that's what you can see here in the graphical representation. This is as I said, this is the normal operation when you have a generator 1 and 2 powering the two AC buses independently. This is when you are using the APU only to generate power. You connect them like this. This is similarly with the external power source. Uh, if you have a fault on the AC1 bus, then you are powered from generator number 2, of course, only because you can't interconnect them, the generators, and that's where everything else gets powered. And of course, the really important systems are powered by they have two redundant power sources from each of these AC or DC buses. So yeah, so there's that. And if you for those who are still around, if you want, we can for the last part we can go over the cockpit just really quickly, how it all looks like. Uh, you have the captain's side, the first officer's side. This is the common area that both of them use. The down here you have the center pedestal that is this place called from here the upper panel. This is called the front panel here, or basically just the upper section. This is called the glare shield, where you have, for example, the autopilot in the middle of that. And yeah, you have the side stick on the sides and the rudder pedals. This is uh, the middle. You can see the primary flight display and the navigation display over there with the most important things you need to see. Uh, this is the ECAM display down here, or actually yeah there, and the other. No, this is from a training material actually. Yeah, and
It was like in approach, but also not in approach. Yeah.
you
It
mean
was in ILS without either the glide slope nor the localizer.
which one? Yeah, yeah, yeah.
It
Those.
says ILS
Yeah,
approach,
yeah. It's a
but
yeah,
no
yeah,
localizer, no glide slope. So
yeah. It's a
what discipline, really?
yeah. This is just a training material, and you have the clock here. Actually, it looks slightly different in the modern versions. You have the lever from for the landing gear. For the this is the brake pressure indicators, the landing gear lock position indicators, and there's a backup and attitude indicator. But I mean these are actually I think those aren't actually fitted on the modern versions anymore. What you can see up there, there's a compass, but you also have a simple mechanical compass actually down in the center. You can just pull this section, this part down, and you have a compass over there. This is the autopilot in the middle. Uh, just a couple words about the autopilot itself. Most people are probably overthinking what autopilot really is. So basically, it's nothing really more than just a fancy cruise control for airplanes, basically. So you you know that even many smaller planes are fitted with autopilot nowadays. You mean when imagine you are in a car and cruising on the highway. I mean, it's not a difficult task to keep a constant speed manually, but it gets boring quite fast. And autopilot basically, well, on top of keeping constant speed, the main purpose of it is to keep a constant bearing and constant altitude. And on its very prime functions, that's all it does. There are two autopilot systems, and there's also the auto throttle that controls the actual throttle levers, and or actually not doesn't move the throttle levers, but it controls the throttle. And yeah, and the autopilot controls the fly surfaces. Yes.
Is the, are the two autopilot systems there because of redundancy for safety, or they're different?
Uh, Also for redundancy, but for example, when you are performing an ILS auto landing, I believe you have to turn both of them on because there are more inputs to handle, and they need to work together. Yeah, this is the breaker panel on the very top. There are also additional breakers behind the first officer's seat in the back, and yeah, this is the certain systems, just to not go really deep into it. This is the engine. Maybe a notable one is the engine fire switches. When you basically when you have uh, an engine fire, it warns you there first of all, and you hear the engine fire chime, and the corresponding engine lights up, and you also get an ECAM memo and things like that. But basically, when you press one of these buttons behind the covers, it basically shuts off all, it disconnects all fuel, hydraulic, and electronic supply from the engine entirely. So to keep it safe, and you also have the option to there are two separate fire extinguishing agents that you can discharge into the engine with each of those buttons. And yeah, there's that. There's the hydraulics and the hydraulics controls that on the top that I talked about earlier. There is also the fuel controls. You don't really have to configure this manually most of the time. There's the electrical panel, the bleed and air conditioning controls. Uh, yeah, that's each. I don't really want to talk a lot about this because this could be worth a whole presentation on their own. Each of these systems really. The audio panel, the radios. You have three different radios. Two of them are on the center pedestal done that you mainly use for audio for communication with ground and other aircraft. And you have a third radio on the upper panel that is mainly used for the navigation as a navigation radio. And yeah, the flight controls, the all the others, and yeah, you have the this is the most bottom part of the center section of the upper panel, uh, where you have mostly the light controls on the sides, all the different external and internal lighting, and that's when you in the center. That's where you can start and actually turn on the APU. Those are the two main control buttons for that. This is the center pedestal with the of course there's the two thrust levers in the middle. You have the trim wheels on its sides. These trim wheels actually turn slower than on the Boeing aircrafts. Uh, and this allows for more fine control, basically, even if you want to trim and turn them manually. And there's the flaps lever and the spoilers, and the two radios here, the audio control panels. This is the transponder, the two MCDUs. Uh, these what control basically the whole process of a typical flight. Uh, you can on this display that's currently shown here. There are the different takeoff speed configured, V1 rotate and V2. This basically also automate the flight somewhat by controlling or giving certain inputs to the autopilots and performing level changes or altitude changes semi-automatically, basically. Yeah, some additional things. This is the ecam panel option switches or buttons, the radios, and I talked about this also. This is the transponder and the two side sticks. And next to the side sticks, do you have these are called tillers. You can use them to basically when you are taxiing on the ground, you can turn the aircraft by turning the nose gear, and you have to use the tiller to turn the nose gear. Yeah, as you can see, it works like there's a button on the middle of it where you press your palm against it, and then you can turn it sideways. And this is the size. These are the side stick. There are not a lot. There are basically two buttons on this. This is the autopilot disconnect slash priority control button. This red on the side, and you have a trigger button on the front that is basically a push to talk to the radio. And I think that's it for today. It's already was a real long session. Maybe I should end this here. If some of you are more interested in it, we can talk about privately about all the other things, maybe. So yeah, thank you for your attention.